Boa tarde. Vamos então passar à talk Modern Systems Programming, Rust and Zig, com Aleksey e Kladov.
Well, hello everyone. My name is Alex, and today we are going to talk about systems programming, Zig and Rust. Okay, so I've been doing systems programming for about 10 years, almost 10 years at this point. Originally, I worked at JetBrains on a plugin for Rust for IntelliJ IDEs. Then I worked on the Rust Analyzer language server, also in Rust. After that stint of compilers/IDEs, I switched to databases. So I worked for a bit in the blockchain, in linear blockchain, which is a blockchain in Rust. And recently, I've switched to another database, TigerBeetle. And surprise, this time, TigerBeetle is written in Zig. So what are we going to talk about today? I have 1 hour, so I won't be able to teach you both Zig and Rust. And instead, we will focus on large, big ideas, large concepts of systems programming, which hopefully will help you to place various languages in your mind more clearly. So what is systems programming? Let me try to be closer to my laptop. So, well, systems programming is unfortunately a confusing term. It seems like it is very crisp and precise, but actually different people might disagree about what systems programming is about. Some common definitions include low-level programming or programming large systems. One definition I particularly like is that systems programming is when the consumer, the user of your program, isn't a human, but, well, another user. All those things are useful to keep in mind. But this talk today is going to be mostly about low-level performance angle of systems programming. And to start, let's look at the history, the short history of the last 10 years of systems programming. So in 2014, we had this vulnerability called Heartbleed in OpenSSL library. It was kind of simple vulnerability, just a buffer overrun. But the consequences were pretty unpleasant. It was possible to get any data from the server running OpenSSL library, a very widely deployed library. So yeah, kind of not a good thing to have. Then systems programming changes, and in 2017, we had Cloudbleed, a similar vulnerability. Also buffer overrun, also in a code base written in an unsafe memory language, and also led to data leaks. Then finally, in 2022, we get a report from National Security Agency which highlighted this problem of memory unsafe languages, which lead to memory safety vulnerabilities, which lead to actual exploitable bugs in software. And the focus of this report was that you could combat this vulnerability by using safer languages. So it clearly is the case that both safety is the issue, and today, right now, we are starting to care about it more than we used to in the past. So we are starting to increase safety of our system software. One thing to keep in mind, though, here is that although those two examples I presented, Heartbleed and Cloudbleed, were pretty drastic, you shouldn't really use outliers. You shouldn't use examples to think about the world. You really want to look at the statistics. But for this case, for security and for memory safety, we actually do have statistics. Companies like Google, Microsoft, Mozilla, they looked at their large-scale C++ code bases. They made a tally of all vulnerabilities in that software, and they tried to count which fraction of those vulnerabilities were related to memory safety. And, well, kind of more than half of vulnerabilities for those companies relates to memory safety. So that means that this is actually important to focus your attention on. So what is memory safety? What makes vulnerability, not just a vulnerability, but vulnerability caused by memory safety? Again, this is something which looks like a precise term, but defining specifically what memory safety is tricky. That is because memory safety isn't a property of an abstract semantics of your language. This is a property of a particular implementation. There could be less safe and more safe implementations of each particular language. So we are going to kind of like give a definition by way of example. We are going to look at some examples of what constitutes a memory safety issue. And the core idea here is that we think about a situation where your program already has a bug. So your program is buggy. The question is, what are the consequences of this error in your program? And in the best case, well, your program doesn't compile. This is like perfectly fine. You just go fix your program, and then it doesn't have this bug. The second case is that the program might crash. So you have a bug, the program compiles, the program runs, but then it crashes. This is, of course, unfortunate from the perspective of the user because, well, they want their software to be correct, to be usable. But from the perspective of security and safety, crash is actually good behavior because if program crashed, then it didn't do anything bad. And the only case where we care about from a perspective of safety is when your program has a bug, it doesn't crash, and instead it does something arbitrary bad. So let's look at a couple of examples here. This is a short C++ function which takes a vector of integers as a parameter, and it contains two different memory safety issues. One is on this line, and one is on this line. So this one is like pretty trivial. We just print 92nd element of a vector, and well, if a vector happens to be shorter than that, we'll just go and print whatever memory is at that location where the 92nd element should be. And kind of like if you look at this, this doesn't immediately look like a vulnerability. OK, so we are printing some memory, and there isn't an integer there, so we are going to print garbage. This is like clearly wrong behavior, like we are printing garbage. But this doesn't look like a vulnerability yet, because this is not a remote code execution, and this is not a denial of a service. The program doesn't crash. It just prints some garbage. But the actual truth is that this is vulnerable, because we don't know what's at that memory. And that memory might actually contain some secret information. For example, that might be a private key, or that might be decrypted data. And basically, both the Heartbleed and the OpenSSL vulnerabilities, they boil down to this kind of like simple buffer overrun. So yeah, that's the second issue here. The first issue here. The second issue here is more tricky. So what is happening here? We have a vector. We take a pointer, a reference, to the first element of the vector. Then we push a new element. And then we print our original first element. And the thing is, because vector is a dynamic array, when we push something onto it, it might actually reallocate its internal buffer. And this might invalidate this pointer. So let's take a closer look here. This is the picture before we run this pushback function. We have our vector, which is a triple of length, capacity, and pointer to the actual elements. And here we have the actual elements. Then when we take a pointer to the first element, well, it basically points to the same buffer. Then we push onto this vector. Because length and capacity here happen to be equal, we actually have to reallocate this buffer and copy over all our elements and add a new element. But then our original pointer happens to still point to this old buffer, which is now freed, which now contains garbage data in the best case, and well, maybe some secret data in the worst case, if, for example, some thread concurrently allocated space for something like a private key, which was reused here. It's useful to think about what is like the core issue here. And the core issue here is that we have two pointers to the same data, and then we mutate this data through one of the pointers to get this picture. And the second pointer becomes dangling, becomes outdated. So there is kind of like two pointers mutation through one of the pointer makes the second pointer go stale. So OK. Let's try to make this a little bit more abstract. What is like the core of memory safety issues. The core is that physically, memory of a process is just a raw array of bytes. So from a perspective of the CPU, from a perspective of an operating system, your memory is just like this array of numbers. However, if your program in some programming language, this programming language actually uses this memory in more intricate ways. It generally allocates objects into this memory. Like your language runtime says, hey, this region of memory is like struct foo, and this region of memory is a pointer, and this region of memory is array. And memory safety issues happen when this logical picture of what should be in the memory gets desynchronized somehow from a physical reality of what the memory stores at this point. So you could roughly classify most of memory safety issues into spatial and temporal. Spatial memory safety issues happen when you kind of like miss the boundaries of an object. So you have some object in memory. You have a pointer to this object. And due to some miscalculation in the addresses, when you try to use this pointer to access the object, you like miss it, and you like get here to some garbage data. Temporal memory safety is trickier. Here, at one point in time, you have an object, and you have a pointer to this object, and the pointer is perfectly fine. It points right into the object. But then, when you use this pointer later, it turns out that the picture has changed. It turns out that this object isn't here anymore. There isn't any more red blob there. There is now like this blue blob there. And so when you access this blue blob from red pointer, you get this desynchronization between what language thinks the memory holds and what the memory actually holds, which leads to all kinds of problems and undefined behavior. Coming back to our original example, this is the case of spatial memory error. We have a pointer to an array. We miscalculated the address of an element because we didn't check the bounds, and we access beyond the end of the array. So this is bad. This case is temporal memory safety error, where we have a pointer to the array, but when we use this pointer, the array is gone. It isn't in this place anymore. It was moved and extended. How can we solve memory safety issues? So spatial memory safety is actually the easy case. Basically, all the objects in program heaps usually either are fixed size, in which case you could just statically check that offsets are in bounds of an object, or otherwise they are arrays. And for arrays, you could fix memory safety issues by just checking the bounds. And important thing here is check bounds here is not something that the programmer does. Bounds check is something that the compiler does automatically so that the programmer cannot forget it. And the second piece of good news here is that compilers today are pretty good at actually eliminating redundant bounds check. So if you compile your program with an optimizing compiler, in the end, you will get only the required amount of bounds checks to enforce safety. And you probably wouldn't lose a lot of performance unless there was like some special case involving SIMD. OK, so spatial memory safety is basically solved problem. Temporal memory safety, on the other hand, is a pretty tricky problem to solve. And you could say that until Rust, we didn't have like a way to reasonably solve it. Like you could even say that like even today, kind of like Rust is not a perfect solution here. But traditionally, traditional solution for temporal memory safety was just garbage collection. Again, the problem of temporal memory safety is that we have a pointer to an object, we have an object, we access the object, but the object isn't there. The object was deleted. So what if we track all the live objects in use and only deallocate objects once we don't have any accessible pointers to them? This works. This is a garbage collection. And you could use garbage collection in a lot of cases. But in some amount of use cases, garbage collection actually doesn't work. And it's important to realize the limits of applicability when garbage collection isn't a good idea. The common myth here is the garbage collection is just slow. And like managing memory manually, it's always going to be faster. This isn't exactly correct. The thing is, modern garbage collectors are optimized specifically for allocation. The allocation in garbage collection is super fast. You usually have to just bump a pointer. The deallocation also is fast because in a moving garbage collection, there isn't actually a deallocation. You just trace live objects and evacuate live objects, and it doesn't matter if you have like gigabytes of garbage. So if your program allocates a lot, it might actually be the case that, well, garbage collection is the optimal way to manage memory in these kind of programs. The trick is, though, that programs implemented in garbage collected languages tend to allocate more. So although individual allocations are fast, the number of allocations tend to be much larger. This is because for garbage collector to work, it needs to be able to walk your heap, to figure out which objects are reachable or not. And that means that garbage collector needs to understand the shape of objects in memory. So that means that language runtime controls what goes into memory. And you, as a programmer, you don't have this extra capability. You don't have this extra freedom to play some nice bitbucket tricks in your memory. You cannot have like full control of how you use the resources. So as a result, the programs implemented in managed languages like Zig, C++, or Rust, they just tend to allocate less memory. They tend to use less allocations. And that is kind of like the reason why they tend to be faster. Not because allocation is faster, but because memory is used in a more frugal way, and there is just less memory to manage. The second reason why garbage collection doesn't always work is that it is like, well, abstractly heavy technology. There are some use cases where garbage collector doesn't fit. And one particular case is composability. So let's say you're writing a big program, and you actually want to write one part of the program in one language and another part of the program in a different language. What happens if both those languages are garbage collected? Well, you get a picture like this, where you have like red lang and blue lang, and they are both garbage collected. And to make garbage collection work in this scenario, a garbage collector needs to actually walk through this heterogeneous heap. Garbage collector for the blue language needs to be able to work to parse red objects to realize that, hey, this one is actually reachable from this one. And well, because each of those two languages actually wants to control the shape of the objects, wants to control the heap, you cannot do this trivially. So yeah, that's kind of like the limits of garbage collection as a solution to temporal memory safety issues. It is a solution. It often works, but it doesn't always work. It isn't flexible enough. So kind of like, can we have something as flexible as C++, but safe? And well, that is basically Rust. The thing about Rust is that if you look at compiled code, then code in Rust and code in C++ are more or less indistinguishable. The big difference between those two languages isn't in the machine code, which is produced by the compilers, but rather in the static analysis, which is done before the code hits compiler, where Rust helps to ensure memory safety. So looking at our benchmark program, the first issue here in Rust will be solved by a bounce check and by a runtime error. So here, Rust will just panic at runtime. It will crash a program. Again, from a perspective of correctness of software, this actually isn't, well, really great. Well, your program crashes. It's still buggy. But from a perspective of safety, this is actually perfectly fine behavior. The interesting case happens here. So for this temporal memory safety issue, Rust manages to catch the error at compile time. This code doesn't compile. And this is kind of like really the big idea behind Rust. Again, I don't have a lot of time to explain how exactly Rust tracks memory safety at compile time, but I want to share just a single core idea. And the idea is this. In Rust type system, compiler classifies pointers into pointers which are exclusive, which means that, hey, this is like the single pointer to this memory, and no other pointer can access this, or shared pointers, meaning that, hey, this is a pointer to an item, but there might be other pointers to this item. And the rule that the type system enforces is that you can only mutate data through the exclusive pointers. Coming back to our example with like 2 arrows and reallocated buffer, this is exactly what happened there. We had 2 pointers, mutated from one of them, and made an access through the other, which was erroneous. And this is exactly that is prevented by the Rust time system. And there are like 2 powerful ideas why this particular type system, well, this particular extension to type system makes sense. One is that this is modular. So Rust doesn't do whole program analysis. It is able to enforce this rule, analyzing a function at a time. The second idea is that this gives you a type system powerful enough to express safe abstractions. So again, as any type system, it not only rejects outright invalid code, but sometimes it actually rejects code which is valid. And as in any type system, in Rust, you have an escape hatch. You have an unsafe, which unlocks a subset of Rust with raw pointers, which aren't checked for these aliasing violations, which you can use to do all kinds of like crazy things. Which is, again, not something unusual. Like all the languages have unsafe in one way or another. The thing which is unusual about Rust is that you could write something crazily unsafe, and then you can wrap it into a safe interface using this aliasing tracking type system to express in a static way what is the safe way to use your unsafe abstractions. So not only you can use unsafe internally, but you can wrap it in an interface which is safe to use and which you cannot misuse. OK, so that is kind of like 2 big ideas why Rust is a successful systems programming language. But it turns out that in the recent years, Rust becomes a successful general purpose language. And one big idea here is that, well, Rust just nails boring things. There is a package manager which just works. There is after formatter. There is like a bunch of IDEs for IntelliJ for everything except IntelliJ. So it's plainly a nice language. And now for something completely different. So consider Python. In Python, there is this idea that, yes, Python is slow, but it doesn't matter. Because you could write your big application in Python, you can like prototype it, and then after your application is more or less ready, you profile it, and you find the 10% of the code which is actually slow. And then you rewrite those 10 slow percent in Rust or in C or in Zeek, and then your application as a whole becomes super fast, but it's still written mostly in Python. So an important thing to realize is that this idea doesn't actually work all the time. There are cases where it is applicable, but more often than not, this actually isn't how the world works. So the trick here is that if you combine high-level language like Python and then a low-level language like C, then when you cross the boundary between those 2 languages, you usually need to have some kind of serialization. You usually need to pay some overhead to transform Python objects into C objects or to expose C objects to Python. So there is like a fixed cost here. If the computation you move from the high-level language to a low-level language is a big one, like, for example, multiplying 2 giant matrices, then this works because the overhead gets amortized over the time savings here. But in many cases, this doesn't work. And a nice story here is VS Code. So VS Code is a text editor for code. It is written mostly in JavaScript. And originally, they implemented the core widget for text editor, which like displays fonts and everything in C++ for performance. And then to improve performance, they rewrote that C++ code in JavaScript. Not because JavaScript is faster than C++, no, it is slower, but because rewriting it in JavaScript allowed these code developers to skip this overhead for transitioning between C++ world and JavaScript world. So although like JavaScript is slower, system which is 100% JavaScript ended up being faster than a system which is like 90% JavaScript and 10% C++. So what does it have to do with Rust? Well, it turns out that Rust, in some sense, is a reverse Python. The same idea works in Rust, but we arrived at it from a different direction. We start from the maximally low-level language with like unsafe pointers and whatnot, and then we write basic safe abstractions on top of that unsafe subset, like hash maps and vectors. And then on top of that basic API, we write like high-level libraries. And it turns out that high-level Rust is actually a pretty pleasant language. Like, OK, it is not Python. Like, I admit that. Like, Python is more concise, more readable than Rust. But it isn't at the same time like completely unusable. Like, it's definitely better than like Java 6, the language we used like 10 years ago for writing high-level applications. So kind of like with Rust, you get the situation where you could write most of your application in high-level Rust and don't worry about performance. And then you can sleep well because you know that if at some point you discover a performance problem in some part of your application, you could actually rewrite your application in a low-level dialect of Rust, and you won't have to pay this FFI tax, which you would have to pay in Python/Rust situation. So yeah. To summarize, Rust is a great language. First and foremost, it's a system programming language which allows you very precise control over memory while at the same time enforcing memory safety. So kind of a combination of memory safety and low-level control is basically what Rust is about. On top of that, well, turns out that Rust is just a decent language. It is like has iterators, build system, smart code editors, whatever. So you could actually write high-level software in Rust, and it sort of like strides this high-level, low-level dichotomy. OK, so if Rust is such a great language, and I like spent like I don't know 8 years of my life hacking on IDEs for Rust, then for what reason I'm right now coding full-time in Zig? Well, to understand this, I need to explain you a little bit about what TigerBeetle is. What is this thing? So TigerBeetle is a distributed database for accounting. And the thing is, like, TigerBeetle cannot fail. We really want to make our software correct. Normally, when you write software, it is OK if your software is not 100% correct. Because, well, let's say you open an application crashed. Well, it's not a problem. You are, like, of course, dissatisfied as a user, but you can restart your application. And, well, hopefully you didn't lose any of your work because everything is securely stored in the database. Except that, well, if you are working on a database, then you don't have this like luxury of just restarting this and starting from scratch. You really need to guarantee correctness. And memory safety is a part of the correctness, important part of the correctness because it directly affects security. But if you do want to make application fully secure and like fully correct, or at least like as correct as humanly possible, you need to go beyond just memory safety. You need something extra. And that extra we use in TigerBeetle is like Tiger style, is a particular set of programming principles which allow us to dramatically increase correctness of the software. Of course, it like doesn't come for free. Like writing correct software is like hard, but there are techniques which you can apply to get like beyond just memory safety. So let's look at those techniques. And like the primary technique is like really like boring. It's just like simplicity, which is like cliche at this point. Like everything in software engineering says that, hey, kind of like to write software, like you need to write simple software. Like a complex system that works started as a simple system that works. Like, and well, the truth is that this really is the case. Like you cannot like work around simplicity. If you want reliable systems, you really need to discover that simplicity. And it seems that in the modern software engineering practices, there really is a huge like gradient of simplicity which you could pursue. And here is just like a simple example. So TigerBeetle is a distributed database. So it needs to talk over the network to other like instances of TigerBeetle. How would you do this? Well, typically, like what you do is like you use JSON, or you use over HTTP, or you use gRPC. but like these technologies are like complicated. JSON in particular requires parsing text, and like parsing text is where like the bugs get you, especially if you are using unsafe programming language. There is also like this nasty JSON-specific thing that objects can be nested. So you need to care about the case where like the input is like nested very deeply, and you don't like and you are not allowed to use recursion there because recursion will overflow the stack. And that is kind of like on the one hand seems like an edge case, but on the other hand, this is exactly like this stack overflow when parsing JSON was something I hit in Rust Analyzer when parsing JSONs from Rust C, the compiler. So kind of like, yeah, JSON is hard. So what we do with TigerBeetle, again, we do radical simplicity. We say, OK, let's say that every message in our system starts from exactly like the same header, which is fixed size. And then we'll just go and cast the slice of raw bytes we received over the network to this header. And like this is our parsing code. Like this is like super simple. And that's what I'm saying when I'm like talking about simplicity. You could really like go from gRPC to here. Of course, yes, this solution has costs. Like JSON is super flexible, super versatile. This solution is like much more rigid and much harder to change. But well, if you care about correctness more than you care about changeability, you might consider something like this. Of course, to do this kind of trick, you need to have well-defined layout for the header, which in Zeek you could do as in Rust using like extern struct declaration. Nothing interesting here. But what's more, you also need to ensure that there is no pattern between the fields. Because, well, pattern in the network protocols like could be used for like who knows what. You really want to nail down every single bit of what is going over a network. And the magic of Zeek here is that you could actually write a simple function in Zeek to check that a struct doesn't have a pattern. So I wouldn't show like the full implementation of this no pattern helper function, but it's basically, hey, we have a type, and we'll reflect at compile time on the shape of this type, and we check that, hey, every struct doesn't have a pattern. This is the kind of code you can't really express in Rust at all. You could express some subset of this using kind of like very complicated proc macros or type system level programming tricks. While in Zeek, this is just, well, straight line, simple code to do what you want. And this is like the big reason why TigerBeetle uses Zeek. Because Zeek is a simple language, not in the sense that it doesn't allow you to do complex things. No, it is simple in the sense that with the minimal language, you still get all the expressivity to write your like crazy performant system software with all kinds of optimizations. And in some sense, you actually like do more expressivity than Rust allows you for. For example, Zeek tracks alignment of pointers, which Rust doesn't, which again, if you are doing systems programming, is something you probably care about quite a bit. So let's go back to our benchmark simple example and see how Zeek fares. So first of all, I would like you to like ignore memory safety and look at like just how frugal Zeek as a language manages to be. So you see like there is no like import statement. When you like want to import print functions from like debug module, you just has like the normal assignment and you have like the normal attribute access without those like double semicolons. Double colons. There isn't like any syntax for generics. So array list is just the function which takes type and returns the type. So again, no syntax here. There is no special macros or special operator overloading for print because again, print is just a function which well happens to inspect this first argument at compile time, but well, otherwise it's just a simple function. So this is like good parts about Zeek. But Zeek also has parts which are not so good. And that part is memory safety. So the first case, the spatial memory safety is like basically solved because, well, we just check bounds here, and it would be like stupid not to do this. So Zeek solves this perfectly. For temporal memory safety, the situation is kind of like, yeah, not really. So if you use some kind of general purpose allocator in Zeek which has extra safety checks, you might have a crash here instead of like outright undefined behavior, but in general, kind of like you need to look out. So kind of like, yeah, Zeek doesn't really solve temporal memory safety. OK, but the fact that temporal memory safety isn't solved by your language doesn't mean that you couldn't solve it in some other way. And if you think about it, well, what's the problem of temporal memory safety? It is when you allocate an object, free the object, and then use it. And the stupid solution is, well, what if we just don't free the objects? What if we just pre-allocate everything we need to, and then just take care to use only those objects? And this is exactly the solution that TigerBeetle uses. So this is the code for allocating messages. Message is kind of like the core data type in TigerBeetle, which is used throughout. And we, at compile time, meticulously compute the maximum number of messages we might ever need. So just summing up all the cases in code where we need the message. Then we go and allocate exactly that amount of messages, and that's it. We never ever allocate any more messages or anything else after the startup. We just go and use only these things because we know exactly how many of those we need. And the cool thing here is that this not only mostly solves temporal memory safety, it also drastically simplifies the software and solves a bunch of other problems. For example, in network services, a common problem is back pressure. If you are not processing requests as fast as the requests are arriving, you might build up huge queues in your memory and die out of memory. Well, if you have the constant amount of messages at all, then you have back pressure by construction because there aren't spare messages to pile up. Similarly, allocating all the memory upfront guarantees you zero copy because you don't have spare memory to just copy data over. You also get faster performance because if you don't manage memory dynamically, you don't need to run allocator code to figure out, hey, where should I put this bit of memory? What else could you do to improve correctness in systems programs? Well, a very fruitful avenue is error handling. There was a very famous paper a couple of years ago which said that for this code path. You make it common case. And that's what we do at TigerBeetle. We abstract our I/O, and we have fake storage, which allows us to inject more faults than we would normally observe from our underlying hardware. So for example, we just say, hey, with some probability, we just go and fold your read. And that makes our error handling code a common case, which is actually routinely executed. If you take this idea a little bit further, you might realize that you might only abstract not only I/O for errors, but you can also abstract away time and create a virtual environment for your software so that inside this environment, you could just run your program faster than you would have run it in real time. So here, as an example, there is a printout from a simulation of a TigerBeetle cluster. So here we see 5 machines communicating with each other. And here we see that machine 1 joins at op 23. It realizes that it is way behind the cluster. It initiates state sync, so kind of copying all the data from other machines to it. And sometime later, it is up to date. And the trick here, because the time here is virtualized, there isn't any kind of timeout. The code here for all 5 replicas runs on a laptop with a performance which is allowed by the CPU without waiting for any kind of I/O, for any kind of external events. This actually happens pretty much instantly. And this is kind of hugely huge multiplicative power for writing correct software if you can run it in a simulation and just simulate years of real-world workload in seconds on your laptop. So that is kind of everything I wanted to tell you today in this 1 hour. Hopefully I am not overrunning too terribly. So to sum up, systems programming is kind of like still hard. There is like still a lot of problems to solve. The glaring problem is memory safety, but if you're doing system software, you probably want to think beyond memory safety. You probably want to increase correctness. Writing correct code is super hard, and you really need to be on lookout for tools which help you write more correct code. And critical tools here are a better programming language, a clearer idea of the amount of resources your program uses, this trick about amplifying rare code paths, or maybe even eliminating rare code paths and making all the code paths safe, and of course this last idea about running your software in a simulation where it can run much faster than in real life. And I think that's it for me now, and I'm ready to answer your questions if we have time.
Hello. What have been the most significant technical or cultural challenges in integrating Rust into the Linux kernel, and how might this influence the adoption of Zig or other modern languages?
Yeah, that's a great question. So the backstory here is that historically, Linux kernel was 100% C, and there was like a lot of pushback against adding other languages like C++. And then like this year, we actually got some Rust in kernel and even some, oh my God, even some real drivers there. So yeah, this is actually unthinkable. It was surprising. I didn't think that this would happen, because the big issue here is that integrating Rust in a system which is written in a single language means that now you have two languages. And irrespective of like merits of having this like more safe language, having two of them is like massively more complicated. Like really, usually the best tool for the job is the tool you already have, as John Carmack said a while ago. So this is kind of like, yeah, really bad. On the other hand, for Linux, the benefits here make a lot of sense. This is a monolithic kernel. So drivers run inside of the kernel, and it's important that like drivers are correct, drivers are safe. You cannot just place them in a different process. So I guess for them, yeah, using Rust made a significant difference, because you could get safe drivers that way. In terms of how this affects perspective of our languages getting in there, well, I think it kind of like complicates things, because managing 3 languages is even harder than managing 2 languages. But I would even say that I don't think there are like many like competitors who like provide a similar benefits, because with Rust you get safety. With Zig you get much better C and somewhat safe, somewhat more safe C, but you don't get like 100% safe C, which is kind of like much less of a payoff. So yeah, I would be extremely surprised if a 4th language is added to the kernel. But well, I'm not a kernel developer, so I'm not the right person to ask this question to. I hope this answered the question.
I'm here. So I'm still a first year bachelor, so when I saw all of these things, advanced things, kind of advanced, I would say, but I didn't understand anything. But I am really interested in Rust and Zig. So how would you recommend us starters to learn those 2 languages?
Yeah, so I would definitely recommend like learning Rust really good, because my prediction right now is that Rust is going to be pretty big language like 10 years from now. So if you are like starting learning something, that like starting from Rust like makes sense, like because it basically it will pay you. In terms of like what's the best way to learn Rust is, well, write programs in Rust. That's it. Like you just like have something you want to do, you do it, and if you like find some roadblock, well, you go to Google, you ask questions on forums, and that way you learn. For a specific problem to use as a vehicle for learning Rust, I would suggest implementing a ray tracer, a program which simulates how the ray bounces off the surfaces and generates an image. So kind of like this is a really nice program which you could do in a weekend, but also which allows you to really like learn a lot of aspects of Rust. But the core idea here is just do it. For learning Zig. So for learning Zig, beware. Zig is not 1.0 language, so it isn't going to be as smooth experience as you would have for Rust. I would still recommend learning Zig because, well, you should learn those programming languages which expand the way you think about software. And Zig, with its comp time, with its allocators which are passed as parameters, with its fresh take on error handling, definitely expands the way you think about programming. So like Zig is worth learning, but that's going to be like a rougher terrain. But the approach is the same. You pick a program you want to write, and then you try to write it. And if you wrote a program, you've learned something, and if you failed, you go and ask a specific question.
Given Rust's recent growth, it's actually been going for a while, and the push for more memory-safe languages, do you think that Zig will have a place in future language space, or will it eventually, for example, die out or just become a way to easily interop with existing C code?
Yeah, that's a great question. I actually made a bet with Joran, the founder of TigerBeetle, because Joran thinks that Zig is going to be bigger than Rust, and I think that Rust is probably going to be still bigger. So it is hard to predict the future, especially it is hard to predict the future of a language which isn't 1.0, so kind of like anything can happen. One interesting aspect here is that kind of like memory safety is not, it's important, but it's kind of like a means to a goal, and the goal is secure software. And there are like different ways you could arrive at secure software. For example, there is like cherry architecture, which allows you tracking temporal memory safety in hardware, and which allows you to run C++ or C code safely. And if that wins, well, that means that Zig has a much higher value proposition. Another idea here is that of like capability-based security. Because, well, kind of like, there is like a saying that, hey, undefined behavior is like nasal demons, like everything can happen. This is not true. Like if you have a bug in your C++ program, it's not true that like, you have demons from your nose because, well, computers cannot do this. If you have like capability-based security, for example, you have at a process level isolation that, hey, this is the decryption process, reads only data from std in and only prints data to std out, you actually like don't care if that might be compromised because it cannot, like it already can produce arbitrary data from input. To safety, and you expose this culture to the internet, which, well, we'll see. Maybe we'll, like 10 years from now, there is going to be similar examples about game dev.
Hi. So I don't know if this question is really within the scope of your talk today, but I was still curious about it. You mentioned that when developing, let's say, Python code, you can replace like the slowest 10% of it by C to make it more efficient. Specifically when it comes to NumPy and matrix multiplication, right?
Yeah.
When it comes to like, let's say, deep learning and specifically computer vision, the subset of deep learning, would it be, since most of the tech stack is like, let's say, most of the companies nowadays use PyTorch for it, would it be or should it be common practice to instead of just basing it on Python, make it more efficient? Since there's a lot of matrix multiplication going on in CNNs and whatnot, should we replace certain parts of it by C? Would it be more efficient? Would it be not okay, not good? So yeah.
Well, I'm like completely not an expert in this domain, so like the true answer is that I don't know. The kind of like more made up answer is that, well, kind of like everything which is based on matrix multiplication in this way or another, like, is already kind of like implemented efficiently in C. So in these domains, yeah, kind of like writing Python isn't actually a liability. The only kind of like problem happens if you need to essentially devise new computational kernels. If you want to do a new kernel, you probably want to write this in a low-level language. And again, if you happen to need that a lot in your domain, it probably makes sense to learn Rust as probably the best language nowadays for writing this computational kernel. Although again, there is this Mojo project which says, hey, let's kind of make memory unsafe subset. Well, I think they claim memory safety kind of let's make kind of fast subset of Python, which again might work. But well, again, I guess it doesn't answer this question. But well, as I said, I don't really an expert in this domain, and I cannot really answer it properly.
Hi. You mentioned that you abstract storage and you abstract most I/O and time in TigerBeetle. I was wondering if this basically implies that you pass some context object to every function call, and that's how you do I/O, and so you basically never touch the standard library. And also, just a follow-up, does this have any performance impacts with, for example, if I don't know if you use dynamic dispatch for this abstraction or if it's all statically typed? I'm curious about that.
Yeah, excellent question. So yeah, this basically boils down to passing the context through everything. And this context is actually comp time parameter. So in terms of dynamic dispatch, no, everything is monomorphized. And there's actually a second reason why we need to do this. All our I/O goes through I/O uring. And I/O uring is integration written by ourselves. So we already are replacing all the I/O, and we have to write something there. One interesting aspect here is that because we write stuff in Zeek, we don't have to enforce this shared store mutable discipline. And that means we don't actually pass this I/O to every single function call. What rather happens is that every large struct in our code base has instance of I/O as a field, and we just use that field. Writing this same architecture, which is again kind of the sea of objects code structure which Rust prevents you from having. Writing this in Rust is probably going to be more painful because you probably would have to pass this I/O as a parameter to every single function. But yeah, hopefully this answers all the parts of the question.
You talked in this talk. You went around this duality between Rust and Zeek a lot. My question is, in which cases, kind of projects, it's better to use Rust, and what project it's better to use Zeek?
Yeah, that's kind of super complicated question. I guess the short answer is use Rust. The longer answer is, well, the first order of business is memory safety. If you don't understand memory safety, if you don't have any plan for memory safety, then well, use Rust. If you do have an idea of what memory safety is and how can you solve this problem in Zeek, for example, in TigerBeetle, we say, hey, we statically allocate everything, so we don't care about temporal memory safety, and spatial memory safety is solved by the language itself. Or for example, you could say, hey, I work in a domain which has a capability-based security, so memory safety is not as strong a requirement because, well, capabilities prevent my program from doing really bad, then probably you already know about the domain enough to figure out whether you should use Zeek or Rust. The second important consideration here is that Rust is a stable language. Rust provides you a stable API. It guarantees to never break your code. Zeek is not a 1.0 language yet. So it might break your code. And again, if you pick Zeek, then you should be aware that, hey, you might fix this code later. Again, for us as TigerBeetle, this isn't a problem because another trick along these lines is that we don't have dependencies. We write all our code ourselves to this same standard. So when a language upgrades, we don't have to upgrade our dependencies. We can only upgrade our code, and that's easy. So what are the benefits of Zeek? Well, the core benefit of Zeek is really this simplicity. And sometimes this extra expressiveness at comp time. So if you are in a situation where you know solution to memory safety which doesn't involve language, and you really need this extra simplicity, and you are willing to eat a pain algorithm of a language, then Zig might be the right choice. I guess one extra thing here is that Zig is not only the language, Zig is also a toolchain for compiling C code. So for example, you could use Zig compiler to painlessly cross-compile C code. And that is actually how a lot of projects use Zig, not as a language, but just as a better compiler for C code, which is like pretty nice use case as well.
Infelizmente não vamos ter mais tempo para perguntas. I would like to thank Aleksey for this talk. A seguir vamos ter pitch às 4h30. Agora vamos ter o coffee break.
Thank you.